Good stuff you have to eat, though. Ozone is spontaneously breaking up in the atmosphere all the time, and it's spontaneously being made all the time. Because when the sun is out, bonds are breaking. Everybody good with this part? Yeah.
When the ozone absorbs UVC, does it like break back up with the single oxygen gas?
Yeah, it does. So ozone can spontaneously destruct by UVC.
It's like a cycle.
Yep, making and breaking in nature. It's totally normal. And you can imagine the relative concentration of oxygen, oxygen singles, and ozone affect how strong the arrows are between those, right? If you're littered with singles, you'll end up with more ozone. If you're littered with ozone, you'll probably end up with more oxygen gas. Make sense? All right. So now we need to deplete ozone. And this is the part where a lot of you will fall off. People who speak chemistry can just look at this and go back to sleep. People who don't speak chemistry, let me remind you that these are clingy. So watch. There are some substances out there, not just this one, other stuff that we've added to the atmosphere. But please look up. When this is struck by ultraviolet heat, a bond will break, and usually the weakest bond is the one that's holding one of these chlorines. As you know, they could maybe get back together, but the funny thing is that ozones are not that stable. When we made a party of 3, some of you might actually have experience with this. Parties of 3 are not that fulfilling, they're not that stable, and they certainly don't last very long. So, this is bound to lose. I'd rather be in a couple than a 3. So, I don't care if Daniel's gone, I don't care if Evan's gone, but for me it's pretty much better to get rid of one of these. Yeah. And make a friend. And by the way, there's no order to that geometry. So they might be just as happy to make a couple and kick me out of the picture. Funny thing is, groups of 3 are not that stable. They're not that sturdy. They don't last very long. So, if that single, please look up, happens to bump into ozone, ozone will kick out the 3rd. Oxygen gas is the most stable and ideal form. And you'll result in this thing, COO. You could say it's 2 clingy singles trying to make things work. But the one last detail that I haven't said at all yet is that chlorine and oxygen are kind of racist. They can work things out for a while, but everybody knows that oxygen is better coupled with another oxygen. So as soon as there's one of these in the atmosphere, and remember, it happens all the time, as soon as COO runs into one of those, the oxygens will combine to make oxygen gas, and we're left again with a single chlorine that will need ozone. That COO is not that stable, so whenever it runs into one of these, it will make oxygen and be single again. Chlorine is like a home wrecker. It ruins an existing relationship, but then it loses interest and ruins another existing relationship. But then it loses interest, and so it'll ruin another relationship. But then it'll lose interest and ruin another relationship. You can visualize this. If our room was 100% ozone, we'd all be dead, by the way, But if our room was 100% ozone with some dead bodies, and you threw in one chlorine atom, in a matter of minutes, it would be 100% oxygen gas. What's that? That's what I meant, a single chlorine.
Yeah,
oh, yeah, yes, exactly. Sorry, you're right. Yeah. If this room was 100% ozone, it would just take a few minutes for the chlorine to break up a threesome, lose that love affair, and break up another threesome, and lose that love affair, and break up another threesome. Yeah.
Would it be
pretty much, because you got to get that single oxygen. I'm almost done, but I'd like to take a break here and see if I can clarify the depletion of ozone. Really? That was all? Now everybody's good with this? Cool to move on? You can do this on the exam?
Do we have to be able to write out all the equations on this thing?
Yes. These are what's called mandatory chemistry by the College Board. So you've got to know that one, and you've got to know that one. Wow, by saying that 1, 2, 3, 4, 5, 6, 7, 8 people decided to take seriously my suggestion to copy the notes.
You've been like standing there.
Well, they can just be making a note of it.
Now, the last thing that you need to know is it's not just CFCs. There are many ozone-depleting substances, anything that spits off a clingy single, especially if it's chlorine, bromine, or iodine, anything that makes a single one of those, when it gets to the upper atmosphere, will be broken up by ultraviolet. And any of those clingy singles can also eat up ozone. It's not just chlorine. So please look up CFCs, the main one being this. Hydrochlorinated fluorocarbons can also lose the chlorine. Halons, carbon tetrachloride, you can see it'll lose a chlorine. Methyl bromide, you can see it'll lose a bromine. And by the way, naturally occurring free radicals, like nitrogen monoxide and hydroxide, this is hydroxide? Yeah. Both of these, which are naturally occurring, can also eat up ozone. You mean to tell me I've got 6 minutes to take a nap right now? Yeah.
Wait, so this in this process is like ozone is made very quickly, and normally it's so like before we were here and before we were producing all these man-made ones and these natural free radicals, did we just keep getting like more and more ozone, or did it reach like a peak?
No, their rates of decay and creation are based on their relative presence in the atmosphere. They get into a steady state equilibrium where the statistical odds of a single oxygen finding another single oxygen are higher, so that oxygen breaks and then just recombines and then breaks and then recombines.
Okay.
Or the odds are higher of it breaking and making an ozone with another couple. That just means what's more likely to happen. Will they be closer to each other statistically, or will they be closer to an oxygen gas statistically? So you get, I think it's called a stoichiometric balance point. Is that the right word? Stoichiometry, where the reactions can go both ways and they get to a balance point based on their concentration. Is that the right word? But do you get the concept?
Yeah.
Yeah, an equilibrium of the reaction. So they decay spontaneously, they're made spontaneously, usually those cancel out. Yeah.
Do the ozone depleting substances ever leave the atmosphere, or are we just constantly adding them?
Evan asked an excellent question. He said, do these ever leave the atmosphere? The short answer is barely and eventually. imagine, most of these will bond with each other because they're clingy and they're single, but they're racist, so they'd rather be with their own kind. So statistically, the odds of one of those chlorines running into another chlorine are diminishingly small, right? But once they have found another single chlorine, or by the way, something else that they stick to, then they will finally be stabilized. They're not, home wreckers keep home wrecking until they find the right person. That's right. Yeah.
So somehow, I mean, obviously we have put a lot of chlorine into the atmosphere because we put all the, CO2 and everything up there.
Yeah.
So it's just going to take a really, really, really long time.
It is. And by the way, we've almost stopped adding chlorinated fluorocarbon. And it's taken about 20 years to see the rate of ozone decline slow down. In the last 20 years, most of the ozone depletion we've seen is just the runaway chain reaction, but they're increasingly likely to run into each other, and so it's starting to drop off.
So when one single chlorine is another single chlorine, and they bond and what?
Yeah, chlorine gas is pretty sturdy. Unless it's struck by ultraviolet C, chlorine gas is forever.
So if there's more chlorine gas in the atmosphere, more of it statistically likely to bond faster.
If there's more singles, they're more likely to run into each other. By the way, we could stop ozone depletion by putting stuff that likes chlorine really well. So a lot of people have said we need to add more nitrogen monoxide to the atmosphere, and coincidentally, the seasonal abundance of NOx in the South Pole is what creates the seasonal cycles of ozone depletion. When there's a lot of this in the atmosphere, chlorine finds something better to do. And so it stops eating ozone. Does that make sense?
Yeah.
Yeah?
Like downsides to doing that? Like,
I'm out of my league. Yeah. Oh, I'm gonna Are we really done? Kids, happy spring.